Maybe.
Should you take this?
Maybe most of.
Oh, no, should you take the microphone?
Maybe most of the transparencies will be folklore for physicists, but I hope that at least one transparency will be new for at least one physicist. And there will be no species in this talk, but there is some species hidden in the talk, but it will not be explicit. Okay, and this comes from brainstorming between me and these four persons. Amel Kaouch is in the room, she has a poster. Cedric Lamat is a young PhD. He has done his PhD with Pierre Leroux and myself on species. Pierre Leroux, everybody knows. This is an undergraduate person which helped us. I don't know.
Faut l'allumer.
Faut l'allumer. How do we do?
Il y a un petit bouton au-dessus, là.
Ah, ça.
Ça s'allume.
Ah, comme ça. Okay, now the light is red. Okay. He helped me, especially in the Maple programs that I will present. We speak about Mayer polytopes and divided differences, but Mayer polytopes are related to one-dimensional hardcore Mayer weights. But I will speak about d-dimensional also things. I recall what is the first Mayer weight of a graph. Here we speak about simple graphs on capital N vertices, and for me, little k is capital N minus 1. It is not the Boltzmann constant. I don't think it is Boltzmann constant. And V is a finite volume, and the first Mayer weight of the graph is this integral for a given f. And this is a capital N fold integration, x0 to xk. Remember that k is n minus 1, so that there is capital N. Here this is volume element, volume element, volume element. And it is very well known that this weight is multiplicative on connected components of the graph, in the sense that the weight, first Mayer weight of a graph is the product of the weights of each connected component. Here this is a S, not a 8, it is a S. Now the second Mayer weight comes from a limit. Mathematicians don't call them this. What is?
In the previous slide, what
Yeah.
was
S?
F?
F. Oh, F is related to an interaction between particles on the positions xj,
It's
x.
any given function.
Any given function we can say. Okay,
Fixed.
any given function. I start with any given function. I don't connect it to statistical mechanics, but it comes from statistical mechanics.
Specialized, right?
It will be specialized soon, but here now it is general, we can say. And there is a limit. If you divide by the volume and you try to look at the existence of this limit, it turns out that intuitively, if you integrate first under the variable x0, then the f doesn't change very much on the volume if the volume is not too big, so that it is approximately the integrand f of x1 xk, and you divide by v, it gives v times integral over x1 xk divided by v, so that approximately it is this integral over x1 xk, and you can fix, because of translation and variance, you can fix intuitively the first variable to 0, and it becomes a k-fold integral. And intuitively, as v becomes big, then it becomes integral over all space. And it turns out that this thing, when the limit exists, is multiplicative on two connected components, which is called blocks also, of the graph C. You see, we start with a connected graph now because of the previous slide. And now the connected graph has blocks, two connected components, and the second Mayer weight, small w, can be computed like that. Now, there are conditions on the existence of this. Previously, we found a condition with an epsilon in this integral. You see the hypothesis on f now is it is defined on non-negative real number, real value. And previously we had the epsilon here, but Alan Sokal told us that we can drop the epsilon. And you see, if we have this, then the limit exists. Usually, I think people, when they work on this, they make this assumption, which is if you have this, you have this. Okay? And for a proof, I don't know where to find a proof other than in our paper. So that if you want to see a proof of this, you look in this paper, which is on the web, under Pierre Leroux. Okay. Now, the usual, the importance of this Meyer weight is that it is important for the virial expansion in the case of non-ideal gases. This is an expression which expresses, this is now the Boltzmann constant, the pressure over K times the temperature in terms of the density, kind of power series, and the coefficients of the power series and the density is a sum, the total sum of weights of the second Meyer weight of all two connected graphs on small n vertices with a constant in front. These are the coefficients. Okay, this is only to show that this weight is important. Now, there has been continued interest from the physicists on Meyer weight, at least for 100 years, I think. And you see there are methods which are approximative or exact for virial expansion, for example, to compute the coefficients. Methods are change of variables, use of symmetries, Fourier transforms, spatial functions, spatial polynomials, spherical harmonic Bessel functions, numerical integration, Monte Carlo methods, etc. Okay? For example, instead of making a full history of these things, which I do not know very well, you look at these two references, for example, and you will have many references about these things. Now, there are methods also which are exact for hard segments in dimension 1. For example, one method uses Erhardt polynomials, and they are good for n equal 1 to 8 particles.
By good, you mean in principle they would work for
They would work,
all n?
yes,
They go
n.
beyond the computer.
Yes, you see, the thing is, yes, the thing is that Erhardt polynomials, if you don't know, it is a way to compute the volume of a polytope by zooming the polytope, and if you count the integral points in the zoomed polytope, then it is a polynomial in the zoom factor, and the leading coefficient is the volume of the polytope. And in the case of hard segment in dimension 1, the d is 1, and the hard segment is in the case where the function which we saw is the characteristic is minus. It turns out that it is minus the characteristic function of being smaller than or equal to 1. Okay, this corresponds to hard
Sorry,
segment.
one other thing. In dimension 1,
Yes.
of course, you can exactly solve the hardcore gas.
Yes.
You get explicit formulas for everything.
Yes.
So you get explicit formulas for each n for the sum.
For the
of
sum.
The weights of
But
all
here we are
connected graphs
interested in
or two
spatial, yes, in spatial, I will speak just after, in spatial cases, that is for given individual graphs, and we want to compute the weight.
But I'm just saying, so the point of what
Yeah.
you're doing here
Yes.
is you have a way of computing for each graph
Yes.
individually.
Yes.
Rather than just the
This
sum
is the
of
thing.
all the
Yes,
connected.
this is the thing. Because the virial expansion in this case is known. I think the coefficients are 1, 1, 1, 1, 1. Okay. And this job has been done by people. Amel Kaouch has done for 7 and 8, and before we add up to 6. And for 8, it is 500 pages of graphs with exact weight each case. This is a rational number each case. Okay, but starting from 9, it is very nearly impossible to do by computer up to now. So that, and there is another method also. Decomposing the polytope of integration, in the case of this, into pyramids and making use of the homomorphic image of the graph in a rectangular grid. I don't give detail, but these are the specialists of this. Okay, and this is good for graphs which are near Kn. For example, the Meyer weight of Kn, the complete graph, is n, the second Meyer weight. Here, you see here, these are references for these things. In my talk, I will speak about the graphs which are near cycles instead of near Kn. So that I will speak about graphs which has not too many edges.
Can I make a question?
Yes?
The title of the very McCoy article you were quoting was telling like understanding the coefficient up to n equal 9 in general dimension for a sphere graph.
Yes, but it is only for dimension 1 we have exact things. Do you think there is, do you know if there is some exact things for dimension up to 9? Or,
So the paper was explaining that it was in some sense numerical also.
Okay, numerically, yeah. Here we speak about exact value, Okay, as Alan said, physicists are mainly interested in summing the weights of all connected or two connected graphs in a given order to find virial expansion. We will focus on the individual graph. And as I said, graphs which are two connected and having relatively few number of edges in one dimension. But I will speak about the dimension in the beginning. This what I will speak now is known probably to every physicist. Suppose I take a connected graph, simple graph on capital N elements, and I take an increasing, and I number the nodes in such a way as we have an increasing covering tree, rooted tree, okay, rooted at 0. And for me, when I have a rooted tree, it corresponds to a function. For example, the rooted tree, I write it in red, the increasing covering rooted tree. And I go
I'm sorry, what do increasing and covering mean?
Increasing in the sense, as you go like that, the number increases.
So everybody points to someone lower number.
Yeah, everybody points someone smaller, okay? And you can describe the covering rooted tree by a function which decreases. The image of 2 is 1, the image of 1 is 0, the image of 4 is 1, etc. Okay? And the interesting thing is, suppose you see the image of 7 is 3. There is an arrow from 7 to 3, and 7 is greater than 3, so that the arrow are precisely the inequality signs. Okay, so that it is very easy to remember. And the complementary edges, I write them in blue. The whole graph is red and blue. At first it was not ordered, not oriented, but it is oriented canonically given the increasing covering tree. And the blue, the edges which are not in the rooted tree, I canonically order them in the same way. 6 is bigger than 4, so that I put an arrow 6 and 4. So that, starting from that, we can make a change of variable. You see, the node x, the node 3 is now associated to variable x3, x2, etc. Each node is associated, node I is associated to xi, and I make instead a change of variable which is associated to the edges of the rooted tree. Okay? And if you start from 2, you call it U2. If you start from 7, you call it U7. Okay? Then if you go from, if I is smaller than j, then you call uj the arrow from xj to xi. And you see it is here. Now alpha I is the image of I, alpha j I mean, is the image of j under the rooted tree. So that here, for example, x5 minus x3 is u5. Okay, these are vectors. Now, it is very easy to see that this is it is a change of variable. You can recover the x in terms of the u if you add with successive images of the alpha function, which describes the rooted tree. You add until you reach 0. For example, if you want to see what is x6, it is u6 plus u5. What is x9? x9 is u9 plus u5. What is x2 is u2 plus u1. I wanted to see one which has 3 things.
Yeah, the first
There
one.
one? Oh, no, the one. Yes, u9, x9 is u9 plus u5 plus u3. Okay, there is one which has 3. Now, if you change each xj by these new variables, it is easy to see that the original integral for the second Mayer weight translates into an integral of this type in terms of the u. Interesting thing is that the u are completely independent. They are completely independent here, as before there, but we'll see later it is useful. And here you see we split the edges. The connected graph is the set of its edges in this context. You split the edges into 2 kinds. The red edges, which give this product, and the blue edges, which correspond to this product. The red edges, you see, if it is x1, x2, then it corresponds to u2, etc. So that the red edges are k red edges because k plus 1 is equal to capital N, and this is a covering tree. And the remaining ones, x6 minus x9, for example, corresponds to u6 plus u5 plus u3 minus u9 minus u5 minus u3. This disappears. So that is our v things. So that I call it v. You go from the beginning to the root and then come back to the other node. So that in general it is this difference, which is a v, a kind of v. Now, is it supposed to? Yes. Now I will use Fourier transforms. While I was preparing the conference, each time I found a new thing, I realized that it is probably known in the literature, but I don't mind. Suppose we have an integrable function from Rd to R. The Fourier transform is this thing. Here it is scalar product. Okay, it is another function of the same kind, not necessarily the same kind, but another function from Rd to R. And under special conditions, it is well known that you can recover the original function by Fourier inversion theorem with a certain normalization here. Sometimes there is normalization constant on both, but I like this way to write the thing. Instead of minus I times the scalar product, we have plus I times the scalar product. And we will assume that for our f, if the f is this one, it is true, that Fourier inversion holds for f of modulus of x, which we call f of vector x. Okay, we'll assume that Fourier inversion exists. And now the Mayer weight instead in terms of Fourier transform can be written in this way. Most probably many persons have done that, but in this way it seems to be kind of canonical way to represent things. The thing is that The Mayer weight can be computed with this constant in front, and the integral here, instead of being k-fold integral, it is c minus a fold integral. So that there are as many integrals as there are blue segments. So that if there are not too many blue segments, the integral is not too big. Okay, and what we compute is for each blue edge, we compute the Fourier. We take the Fourier transform with a variable associated to the blue edge, and for each red edge, we have this. This I will explain. We have a product of indexes from 1 to k, and suppose nu is an index from 1 to k, that is a node of the original graph. You take the subgraph induced by this node, I call it A nu, subgraph. A0 is the whole graph, okay? The whole tree, I mean. I take the subtree associated to vertex nu, I call it A nu, and I take the Fourier transform of this difference. This means A nu smaller curvilinearly to A means that the edge, the blue edge, enters the rooted tree, but its extremity is not in the rooted tree. And this notation is the reverse. The blue edge E comes from the rooted tree and goes outside. If we take a blue edge from inside to inside, it cancels in this difference. Okay, so that the way to have the weight, Mayer weight, using Fourier transform is to compute this integral. Okay, and I will give a short proof of this. It's a short proof. I start with this way of writing the things with the UJs, UIJs, and if you use Fourier inversion to evaluate these V's, it turns out that by Fourier inversion you can write the f of the V's in this way, because this is the x where you compute the value. You have variables Tij, and ij is blue, so that this is Te of some blue variable. And the thing is, if you substitute for this expression in this integral and manipulate the integral, this is some care, one needs some care for that. Perhaps I would have to put the two transparencies to give the detail. It turns out to be the formula. Now for hard spheres in dimension d in general, that is the function is minus the characteristic function of the modulus of the vector in d dimension, which is minus 1 is if the vector is in the unit bar, 0 over 1. It turns out that the Fourier transform of the unit bar is this, with the Bessel function. And the previous formula comes in this way. You see, in the hardcore in dimension d, this is the general formula for the Mayer weight. You see, the difficulty is in these differences. If we had only this to integrate, this would not be too difficult. But we have this. And if you take modulus of things which are differences, then you need some change of variable in d dimension with spherical harmonic, things of this type. Okay, so that this is the thing which make it difficult to compute for particular graphs. Okay, one example which I think Katsura has found after I found that, I realized that somebody knew that in advance, is in the case of ring diagram. You see, in the case of a cycle, we can take the covering tree to be 0, 1, 2, 3 like that, and the blue edge is only one edge, so that the integral will become one fold, because c minus a is one element. And now, if you look at this formula, you will find that it's simply the weight of the cycle, n cycle, is simply this integral in terms of the Fourier transform of the original f. This is a general formula for cycle. And why? It is because, you see, there is only one edge in C minus A, this is this edge, okay? So that if you look in this product, you will have f of t index this edge. But each difference is minus this edge. If you look at the definition of entering and going out, you will have each of these k factors to be f of minus arrow t. And there will be k factor having f of minus arrow t plus and another one with f hat of t. So that it gives in total n factors of f hat of t, which is this formula. Now, okay, this, using Maple, I found from, perhaps I've done too transparency. Yeah. You see, if we take the case of hard spheres, that is with this, with characteristic function, it turns out since Bessel functions gives Fourier transform for this case, this is the explicit expression for the weight of the cycle in n dimension, in d dimension. And this, using symmetries of this expression, this is symmetric about on sphere, it becomes a single variable, one variable. Okay, this is the expression, explicit expression for the Meyer weight of ring diagrams in d dimension for the special case hard sphere. Now, I have used Maple to find asymptotic of that, because when you send integral raised to a power, everybody in asymptotics knows that the Sardel, not the Sardel, but the Laplace method is good to find the asymptotic expansion. Okay, but it took from with me. This is the first time. Okay, the W in dimension d of the cycle is minus 1 to this power times this times this. This is the volume of the sphere to the n and n to the minus half of d. But using Maple, it was very long. Using Maple for about 10 pages of computations, I found that the correcting terms are these. Okay. And the funny thing is that there is a d minus 2 here. This is interesting. It means that in 2 dimensions, asymptotics will be very precise if we drop this term and we keep only the first 2. It will be as precise as if we continued with n cube. Okay? And I made a table using Maple. Maybe I don't wait
I
enough.
suppose there's a d minus 2 in the next one as well.
What?
Do you know if there's a d minus 2?
No. I check. Actually, I computed 10 terms approximately. Okay, there is no d minus 2. I was expecting that. No, I would have been surprised if there had been a d minus 2 everywhere. Okay, and for d 1 to 4, you see these are the terms. Dimension 1, dimension 2, dimension 3, dimension 4. Dimension 2, you see, there is no n minus 2. The next one is n minus cube. Okay? And it turns out there is a root each odd dimension, and there is no root each even dimension. This is a general thing. For the cycle, the Fourier transform is in terms of Bessel functions. It turns out that this is trigonometric functions in odd dimension. The Fourier transform of this in odd dimension, it is expressible in terms of trigonometric function, and it is easy to compute explicitly with integrals. But the funny thing is that for 2 dimensions, the asymptotic is very easy. Now I will go to 1 dimension. You see, with 1 dimension, we integrate over r instead of r to the d, and we don't have arrows on the variables. Now, I write the general formula here. It turns out, it is very well known, that the Fourier transform of this function is this expression, so that the formula in terms of Fourier transforms becomes this one. And it turns out, you see, if you look at the numerator, you see this is a product of sign of linear combinations of variables, so that it is a trigonometric polynomial in the variables. And under, this is a polynomial, a product of linear expressions, so that it is a polynomial in the variable also. Okay? So that the Mayer weight, if we rename the variable, instead of writing a variable for each blue edge, I write T1, T2, Tn. N is the number of blue edges. Okay? So that we have to compute an integral of this type, given a trigonometric polynomial on the top and an ordinary polynomial on bottom. I've done my PhD many years ago on complex analysis, so that I said to myself, is it easy to compute this? It turns out to be easy. Perhaps physicists know that, but at least for me, I found it was easy to compute one by one the integral. First, I will need to define what I call a generalized trigonometric polynomial. You see, the numerator was a trigonometric polynomial, but I need a more general notion to integrate successively the formula. I need a notion which I call a generalized trigonometric polynomial. You see, it is a trigonometric polynomial. Usually there is no, in the coefficients, there is no variable. The variables are only on the exponentials. But here I need polynomial coefficients in the variables. That is why I call it generalized. I could have called, how is it called? Exponential polynomials of trigonometric type. I could have called it like that. But I call it general trigonometric polynomial. And it is well known that a trigonometric polynomial or a generalized trigonometric polynomial is real if and only if you, oh yes, and the indices are real numbers instead of integers, okay? It's more general than I thought. It turns out that I need real numbers for the indices. And the generalized trigonometric polynomial is real if and only if you change the sign of each coefficient of the index of each coefficient, it gives the conjugate. Pardon?
Your coefficients are polynomials.
Yes. Yeah.
Then you just take the link of polynomials over R.
Yeah.
So your
No, but it may be
polynomials are
no,
over
maybe the polynomials are complex value. You see, because maybe they are complex.
Extend the field. They field
But I need polynomials with complex values, and I need okay. But a special case is when it is real. Maybe it is sufficient. I'm not sure. Okay. So that okay. Now I gave a definition. The adjoint of I will take one variable generalized trigonometric polynomial now. The adjoint of a real generalized trigonometric polynomial, I defined it as with the coefficient c mu star, which is I times the signum of the index, which is a real number, times the old coefficient. In Zygmunt, I saw in the beginning of the book of Zygmunt, he puts a minus for ordinary trigonometric polynomial, but it will be better for me to put a plus here. It turns out if you write your generalized trigonometric polynomial in the standard form, that the adjoint is the same, but no constant term, and the a nu is replaced by the b nu, and the b nu is replaced by minus a nu. This is something which is normal in this field. Now I will need divided differences. I recall what it is. You take a function and you define the zeroth divided difference by the function itself at the point. For 2 points, it is well known. You define it as the slope of the function. 3 points, you can define recursively like that. There are many ways to write this recursion. You take the last two minus the first two, divide by extremes. Then for this, you take the last 3 minus the first 3 divided by the difference of the extreme. And in general, it is easy, it is well known also, that the divided difference is a linear combination with coefficients related to the xi, xj of this form. Okay? This is distinct point, but there is the confluence case where points are repeated. I write xi to the mi to represent the sequence xi, mi times. And now I define, which is one way to define, the confluent case of divided differences by using partial differential operators on the non-confluent case. This is a standard way. And one motivation, which is, if you don't remember this formula, one motivation is to remember this formula. This formula from complex analysis gives the divided difference for the distinct points because it satisfies the same recurrence. Here the contour is around all the points. And now, if you differentiate this formula in this way, the exponents will come. So that it is natural to define the divided difference in the confluence case by using these differential operators. Now we see what happens in the case of confluence. For example, 3 times the letter A, 2 times B, 1 times C, is that A has been used 3 times, so that there are up to second derivative involved. Each time there is the derivative and one less than the number of repetition of the variable. But interesting thing is that these are all rational functions in the AI, ABC as coefficients. Now, okay, now I have an integration lemma which comes from classical complex analysis. It is, for me, it was new when I discovered it. Maybe it is known. Consider a real generalized trigonometric polynomial that is in one variable, it satisfies this. And this will be the numerator of an integral. And the denominator, suppose it is a polynomial. And suppose that the integral of the integral I consider is pole-free. That is, every root of the numerator is cancelled by a root of the denominator. Okay? It turns out, for example, sine t over t is a special example. Very trivial example. You see, if t is 0, then sine t is 0. This is a continuous function, things of this type. Okay? To compute this integral, you need simply to, I will give a short proof after, you take pi times the divided difference according to multiplicities of the root, at the roots of the adjoint polynomial of the t. And it works every time. And in our problem, this was trigonometric polynomial on numerator, which was cancelled by the denominator because it was a product of sine t over t. So that this will be a useful lemma. A sketch of proof. Not completely trivial. This is not completely trivial to prove that. You see, from the trigonometric polynomial, I consider the analytic function t of z, which I define as t of z minus I times t star. I call it u of z. It turns out from the definition of t star, which was using the signum function, it turns out that for the generalized trigonometric polynomial, only the indices which are strictly positive or 0 enters. So that this is an analytic function. If I call v to be not the conjugate, but perhaps it is a conjugate because this is real, this is real. Okay, you put plus I, it gives the negative indices which are used. So that if you take the average between u and v, it will give t. Okay, t is the average between u and v. Now, I use residue theorem to compute. I take this half disk with indentations like that. I integrate u on this half disk. By residue theorem, it is very easy. It is 2 pi times this, because the integral of t is 0, because there is no pole for t. And it comes only 2 pi I, the integral of minus I t star. 2 pi I times minus I t star is 2 pi t star. So that it will give as if we had minus 2i pi t star here, and cancelling the i's, it gives 2 pi times for t star, the value of the integral. But the value of the integral is a divided difference. So that this integral is equal to this. Now, with the under the answer this, with the same path on linear on the rees, then it is 0 for the v. Now I add this one and this one, I take the average and the limit as the half disk goes to infinity. Since the average of u and v is t, and it is easy to see that the integral here for this is 0 when the circle increases. Integral at the limit of this upper half circle is 0 when the radius increases. It is easy to see that we will have twice the integral over the line, and so that we will have this plus this is twice what we are searching, because this will not move as the radius increases. So that the average of this and this is only pi times the value. Perhaps some specialists about trigonometric polynomial will say this is trivial, but it is very interesting, at least for me. Now, if we use the integration lemma n times, then we will hope to be able to compute the value. You see, this was this was at the beginning a trigonometric polynomial in the usual sense. Polynomial. Here I integrate t1, t2 using this lemma. Okay. Now, some acceleration can be achieved by replacing t star by u. It is easy to see. You see, u has less terms than t, so that some acceleration, because you see t goes from negative indices and positive, and u has only positive indices. That some acceleration can be achieved by, instead of using this, you can use this. Don't get details, but okay, just to illustrate a simple example. Suppose I want to find the Meyer weight of this graph, second Meyer weight. According to the formula, it is this. If we integrate relatively to t1 using the lemma, you see there will be some variables in the coefficient. It is why we need generalized trigonometric polynomial. This is a trigonometric polynomial here, but integrating by t1 gives a generalized trigonometric polynomial, that is, there is in the coefficient some variable. And if you integrate another time, it gives a well-known value, 14/3. For example, in wheels, you can take as the increasing rooted tree, the center of the wheel, and the blue things are n blue arrows. And the formula is this for the wheel, and with the convention tk plus 1 equal t1. It is easy to see that the general formula in this case is this. And to see the force of this weight, of this approach is, for example, up to wheel 24, actually I've put the button of my computer in the evening, and the morning after I saw the output. But I think this few minutes, up to 9 approximately, a few minutes computation. And you see it is very explicit. These are the exact values for weight, for wheels. And if one has taken Erhard polynomial to compute for 24, for example, we need this number of points to be tested in the Erhard, so that it is not feasible with Erhard polynomial. Maybe this is the best way to compute some for certain graph. For example, generalized wheel. Generalized wheel is a wheel where the radius are different and the arcs are different. It turns out, you see, the increasing rooted tree, I did not put number. Increasing rooted trees are like that. And there are very relatively few blue arrows, so that the integral will be not too big. And the wheel I classify as the radius and the arcs. For, I think this is this one, this is this arc. Arc is the length, 1, 2, 3, 4. 4 radius, 4 arc. 3 radius, 3 radius, arc number, length 3. And in general, if you have the radius r nu and the arcs alpha nu, it is easy to, and if you have k radius, it is not difficult to see that the integral is this way, so that it can be computed also for this case. For ladders, for example, ladder for me doesn't have legs here and doesn't have legs here, because with Meyer weight you can chop the ends, the legs, and you have contribution 2, contribution 2, contribution 2, 2, it gives 16 times this thing. So that, suppose the ladder has 5, as k, for example, k steps, then we can take the increasing rooted tree like that, like a comb, and the blue is this, the complement of the rooted tree. It turns out that the function, now I described with the function giving the rooted tree and the complementary. The function giving the rooted tree, you see, 1 goes to 0, 2 goes to 0, 0, 0. 3 goes to 2, 4 goes to 2, 2, 2. Okay, this is a way to code the increasing rooted tree with ladder of k steps. And the complementary is very easy, 1, 3, 3, 5, 5, 7, this. I've made a program, you give this as input, and it gives the Meyer weight as output. You see, this gives the table. You see, for 20, this means that there are about 60 edges, because 20 like that, about 20 like that. So that it is 60 edges. This is not pi. This is 60 edges approximately at the end, and not too long with even my small computer to have this thing output. I wanted to prepare something with the time, comparative time, but I did not have time to find comparative time. I will give you a feeling of the program, and I will end with 2 challenges about asymptotics. So that I will give 2 challenges about asymptotics at the end. The program is, you see, it computes the weight of a graph. I've not optimized. The covering rooted tree is given as a list, as in the case before, and the blue edges are given as list of pairs of elements. I is supposed to be smaller than j to be canonical. You see, there is a program, I will go very rapidly. There is a program, a procedure giving the divided difference in the distinct point case, a procedure giving the divided difference for repeated points, a procedure to clean one term by using only exponentials where index is greater than or equal to 0, a procedure to change the trigonometric polynomial into one which uses only greater than or equal to 0 indices, a procedure to compute integral p over p using these divided differences, a procedure which determines the descendants of vertex j along a rooted tree, a procedure which computes the vertex set of the induced rooted tree a nu. I need all these things to implement. A procedure which computes the sum difference. Remember the sum minus another sum in the transform. This is trivial one, which gives the Fourier transform of this function. A procedure which computes the integrand. A procedure which computes, this is technical one. This procedure is compute the Meyer. You put the increasing rooted tree in the form of a list, and the complementary in form of the list of a list of pairs, and it uses all the things to compute the Meyer weight. Now, this is the challenge I put to specialists of asymptotics. I put a challenge. Find asymptotic estimates. The challenge is, at least for me, find asymptotic estimates for the Meyer weight of some one parameter family of graphs. For example, as k goes to infinity, what is the asymptotic value of the integral of the giving the Meyer weight of the wheel k? The problem with this, it is the number of integrals increases with k. If it were only one integral, then Laplace method could be used, but there is, I will show you again the integral after. But you see, in these two cases, the number of integrals increases with k. And I want the asymptotic expression in terms of k, which is a number integral, and it enters in the integrand also. This is the problems I asked, but I will say this at the before, and then I will go back to the integrals I asked. For example, this one. What is the asymptotic of this? You see, there is a k factor. So that's not saddle point, but Laplace method, I don't know how to apply in this situation. Because k is the number of integrals, and I want asymptotic with respect to k. Is there somebody having an idea how to compute that asymptotically? I don't know. I think this is the end. Yes.
Question? I have a couple of questions. Well, one of them is, now that you have the weights of all of these graphs up to order 9,
Yes.
I was wondering if you could look for bounds of the form sum over class of graphs is less than the sum over the minimal representatives of those graphs. We know that sum over all graphs is less than sum over trees, and I know of one other example where that happens in some other context, but I've never been able to figure out what the right way to formulate, for instance, two connected graphs, whether they would be bounded in some nice way by some smaller minimal class.
We did not have found time to study, but perhaps he can send you a table, 500 pages of weights with the graphs. Also, there we have.
The email would be shorter if David sent her an email with the question.
yes, because she will try to answer. She will try to answer. I don't know exactly what to say, but we did not have found time to study the list. It was long enough to produce the table. Yes, but...
Okay, I have one other question. That is, the theoretical physicists would have probably assumed that the function f was a function of the x minus y squared rather than the x. And I know that you've already done some the case where it's Gaussian,
yes.
right?
In
so
one of the papers with Pierre.
Yeah, so you can evaluate the Gaussian, because it's a Gaussian integral, that'll come out in terms of a determinant, which is a sum over trees or something like that. Is there some reason why you decided not to go that route here? Is it better somehow to think of it as a function of x minus y absolute value rather than x minus y squared?
I don't, because we are not physicists, we are only mathematicians. we wanted to study.
So what's the difference between looking at
you
norm
mean
or norm
not
squared?
putting squares?
Norm squared would give you a Gaussian integral in the x variables, which you could then evaluate exactly in terms of the determinant. That's the graph, the determinant of Feynman. That's the, I forgot what you call it.
No, but I don't understand. I mean, F is some rotation invariant in translation invariant potential,
Right.
but it might not be Gaussian.
Exactly, but F
It's just hardcore.
But if you assume it's a function of r squared, you can write it as the Fourier transform of
something like that.
e to the I t r squared.
Oh, I see. Do Fourier transforms
Yeah,
in our
something
squared.
like that.
And then you
With
can,
matrix also.
right, so you'd have to have a complex one, it would be e to the ITR squared instead, but then you can
Yeah.
do that integral.
Yes, I see more easily.
Yeah.
Because you see, the hard spheres are also interesting, perhaps for physicists. But
They are, yes.
yeah, and
You mean, so you write the arbitrary potential as a complex superposition of e to the ITR squared.
yes, okay, yes, I thought, but I never done.
But then he'll have an integral with some horrible
Because we know
determinant.
explicit
It'll
for
have a
Gaussian.
horrible determinant, but it'll be a sum over trees, and
Yes, I see.
so maybe you
This
can do
is
something.
I will explain this to her.
For your problem of asymptotics,
Yes, do you have an idea about
so do you think that your sequence is definite?
sequence? Oh, I tried a little with Maple to see if it is definite. I found nothing, but maybe I did not try correctly, because with
you
to
have
check
24
definiteness,
terms?
one must put the parameters correctly. Sometimes maximum degree of polynomials. And
Yeah, but one doesn't know in
it's
advance.
delicate sometimes. Sometimes it doesn't answer even for simple sequences. Sometimes. 1, 2, 3, 4, 5, 6, for example, natural number. If you don't put the good parameters in G fun, for example, it doesn't give the natural number as the answer. But yes, I tried a little bit. But this would be very interesting.
What about the Legendre transform? Does the
Then what-
Legendre transform? If
This
you
I
use them
don't know,
in-
I don't know these things. Pierre Leroux know some things, but
Because sometimes you can use a Legendre transform to get the two connected part of the pressure, and you can get the two connected from that. I don't know if that works here.
I don't know.
think you want to the
I don't
vertex,
know.
two vertex connected, or two edge connected.
I don't know.
But in his case, he knows the sum of all the two connected graphs.
Yes,
He wants to
the
compute them
sum we know.
individually.
This is individual that way.
In one dimension, he
Individual
knows everything.
Oh,
graphs.
he knows even the sum of the two connected graphs as well.
Yeah, because he takes the
Yes.
solution of the one-dimensional hard.
Is it with vertices or with edges?
Yes, this is done. It is known
Which notion of
since a long time.
I guess it's vertex connectedness for Mayer graphs.
Yes, is there some combinatorial interpretation, for example, in this, for a general case, what is, I mean, for this case, for general graph, is there combinatorial interpretation of the weights? We don't know. We are unable to compute, but we did not find a simple combinatorial, as in the this Laplace case.
Yeah, you might be able to, well, I'll tell you afterwards, there might be a way
Okay.
to get asymptotics
Okay, very good.
of ladders.
Okay, thank you.
Any other questions? Okay, if this is not the case, then let us thank
Okay.
him again. And all the